In the next few videos, you'll see how to find a maximum flow in a flow network. Now, a flow network consists of a weighted directed graph where all edges have a non-negative integer edge weight. Now, the weight of this edge is called the capacity of that edge. And there are two distinguished vertices, the source vertex, which in this case is S, and the sink vertex, which in this case is T. Now the source vertex has no incoming edges, it only has outgoing edges. And the sink vertex has no outgoing edges, it only has incoming edges. Now a flow network is often used to model the distribution of a commodity, like electricity or water or some other utilities or manufactured parts, etc. And how that commodity is distributed from one location, the source, where the item is created or distributed from, to another location, the sink, where that item is to be distributed to. So for example, this could represent a water flow network where S is a water tower that has many pipes connecting it to various parts of the city, ultimately to be distributed to your house at location T. But each pipe has a different capacity, and it can only hold so many gallons of water. Some pipes can hold 5 gallons of water at a time, others can only hold 3 gallons of water at a time. Now, on this network, we can model how a flow of some commodity travels through the flow network. So this is accomplished by specifying a non-negative integer for each edge. This is in addition to its capacity. So this integer which we assign is called the flow for that edge. And this represents the amount of a commodity traveling through that edge. But it must satisfy two rules, the capacity rule and the conservation rule. Now the capacity rule says that the amount of flow that an edge has can't exceed the capacity of the edge. So to go back to our water flow network example, this would be that we can't send, if a water pipe can only hold 10 gallons of water, then we can't send more than 10 gallons of water at a time through that edge. Now, secondly, the conservation rule says that the amount of flow going into a vertex is the same amount as going out of a vertex, with the exception of the source and the sink. So that's to say that there's no amount of flow which is lost or gained as it goes from the source to the sink. So for example, in this network where we've already have flow values assigned, so this is in general, this is flow over capacity. Here we have a total amount of 5 gallons of water going into vertex W, and we also have 5 gallons of water going out of vertex W. So with the exception of the source where we're getting our commodity from and the sink where we're sending the commodity to, for every other vertex we don't lose or gain any commodity along the way. However much is going into a vertex, this is the same amount as what's coming out of the vertex. This is the conservation rule. Now the value of a flow, which is denoted this way, this is the total flow from the source. Now because of the conservation rule, this is the same amount as the total flow into the sink, and equivalently the total flow going into the sink and coming out of the source. So for example, on this graph, the total flow F is 8. This is how much is coming out of the source, and this is also how much flow is going into the sink. So for a flow network, this flow is said to be maximum if its value is the largest of all possible flows. So for example, here is an example of a flow assignment set to this network. The flow value of this is 8, so this is how much is coming out of the source. This is also how much is going into the sink. But this is not maximum, because instead we could increase this flow in some way, and this is shown in the below graph. Exact same graph, except we've changed the flow value. So here we've increased exactly along this path, in fact. We increased how much, let's say, water we're sending from the source to the sink. So the flow value of this graph is 10. Now our problem becomes, given a network with a source and a sink and edge capacities, find a maximum flow. So we want to assign flow values to each edge, satisfying the conservation and capacity rules from the previous slide, which maximizes the flow of the network. So for example, in a water flow network where vertices represent different capacity pipes, we want to find the maximum amount of water that can be routed from a given starting point to a given ending point. Or to give another example of how this could be applied, say a company owns a factory located in some city X where products are manufactured and need to be transported to the distribution center in city Y. And you're given all the one-way roads that connect pairs of cities in the country and the maximum number of trucks that can drive along each road. And you want to determine the maximum number of trucks that the company can send to the distribution center. Now this can also be applied carefully to solve other problems such as finding a maximum matching between two sets. So for example, you have a set of students and dorms, and each dorm is a little bit different, has some different features. And each student has a list of which dorms they would prefer to have. Maybe this student would be happy with dorm 1 and dorm 2, and this student would be happy with dorm 2 and dorm 3, and this student would be happy with any one of the last 3 ones. Now, in order to find a maximum matching, this is the most number of students that we can pair with exactly one dorm satisfying their preferences. We can solve this by finding a maximum flow, and that's essentially by adding one source vertex attached to all students and one sink vertex attached to all dorms. Now, we'll also see that in order to find this maximum flow, we need to obtain a specific partition of vertices known as a cut. Now, this partition of vertices is also used to solve image segmentation problems. So given an image, we want to separate all of the pixels into either the foreground or the background. And this is useful for image processing and image manipulation, also, let's say, for self-driving cars to distinguish between, the foreground pedestrians and stop signs from the background of things that aren't as important for the car to pay attention to. Okay, now, as I mentioned, finding the maximum flow in a graph is closely related to finding a cut with minimum capacity. So what is a cut? This is just a partition of vertices so that on one side we have vertices including the source, and on the other side we have the remaining vertices including the sink. So here we have vertices in green are one part of this partition, and the vertices in blue are the other part of this partition. So we could draw a cut this way as a line across edges, because every edge then, which goes from a vertex, connects vertices from these two different sets, kind of describes this cut, this partition of vertices as well. So edges we could classify as either forward edges, they go from this set VS, which includes all those vertices including the source. So these are forward edges, they go from, in this case, from a green vertex to a blue vertex. Or back edges, which go back from this set VT, set of vertices which includes the sink, back to a vertex of VS. Then we can define for this cut a flow as the total amount of flow sent across this from VS to VT, which is how much flow is being sent along a forward edge minus however much flow is being sent back through this back edge. So for example, in this network where we've assigned flow values, the flow of this cut is 8. This is exactly 2 minus 1, which we're sending back, plus 3 plus 2 plus 2. Whereas the capacity of a cut is the total capacity of forward edges. This is how much flow we could send across this cut, the maximum amount of flow that we could send across this cut. So the capacity of this cut is 24. This is 6 plus 3 plus 9 plus 2. We're not including this edge because this is a back edge. We can't send any flow across from VS to VT through this back edge. We can only send flow across forward edges to get to T. All right, so I mentioned now that finding the maximum flow is related to finding a cut with minimum capacity, and this is largely because of these two lemmas. Now the first lemma comes from the conservation rule. it says that the flow across any cut, we could have many different cuts across a network, but that the flow across any cut is equal to the flow value. And again, this is because we don't lose or gain any flow along the way. So the flow of this network is 8. This is how much is coming out of the source, which is the same as how much is coming into the sink. And the flow of this cut here is also 8. This is 2 plus 3 plus 1 plus 2, those flow values of those forward edges. And the flow of cut x2 is also 8 because we didn't lose anything along the way, which is 1 plus 3 plus 2 plus 2. Now the second lemma comes from the capacity rule. It says that the flow across any cut is no more than the capacity of that cut. We can't exceed the capacity. So for example, the capacity of this cut is 12. This is 6 plus 3 plus 1 plus 2, whereas the capacity of this cut is 21, 3 plus 7 plus 9 plus 2. And in each case, we don't exceed the capacity of either one of these cuts. But then, since this holds for any cut, we can combine these two lemmas because we know that the flow of any cut is equal to the capacity, is equal to the flow value. So the flow value can't exceed the capacity of any one cut, including that cut that has minimum capacity. Okay, we'll see in fact that the flow value of our network is equal to the minimum capacity in the next video.